Hello and good day everyone, my name is Ron and let us answer some heat exchanger problems. Create a shell and tube heat exchanger model in DWSIM for the following parameters. The compounds are toluene styrene using the property package Unifac, where the cold in a stream is pure toluene with a 50,000 kg per hour mass flow, 308 Kelvin temperature and 6.5 bar pressure. For the hot in a stream, it's pure styrene, 70,000 kg per hour, 400 mass flow, 423 Kelvin temperature and 3.5 bar pressure. The flow is in countercurrent configuration and the type of heat exchanger is a shell and tube. The number of tube passes is 16, number of total tubes is 1024, tube spacing 75 millimeters, tube layout square, thermal conductivity of tube 70 watts per Kelvin, tube roughness 0.045 millimeters, fouling factor 0 Kelvin meters squared per watts, tube length is 5 meters, external diameter for tube is 60 millimeters and tube thickness is 5 millimeters. In the shell part, their number of shell passes is 2, fouling factor is 0 Kelvin meters squared per watts, shell internal diameter is 990.6 millimeters, baffle spacing is 250 millimeters, baffle cut is 25%, and fluid in the shell is the styrene. And note that the shell fluid, styrene, is also considered as the hot fluid. So the questions are, what is the overall heat transfer area for the heat exchanger? What is the amount of energy transfer? And determine the thermal efficiency of the heat exchanger. Now to start, this is the diagram, summarized in all details, and the required is as follows. Now, let us simulate using DWSIM. So, we need to create a new process model and do the following general procedure for every DWSIM operation or simulations. Now first, we click next, then we need to add the properties. So the property earlier is toluene and styrene. So double check toluene and styrene, okay. Next, and then the property package according to the problem, it uses Unifac. So we'll put here, search for Unifac. There you go. Next. And then we'll need to make our own unit system. So the unit system is, for the mass flow, it's kilogram per hour. No change there. For the temperature, it's Kelvin. So we'll put here Kelvin. And then for the pressure, it's in bar. And then we'll also take the pressure difference as bar as well. And essentially, that is it. So the rest of these details, the units are specifically stated and adjusted when we try to edit the shell and tube. So there's no need to change it in terms of this system of units. So that is it. Then we need to go to the reactor, exchanger. Click heat exchange. And the beauty of this update is that it automatically prepares the streams for us. So we'll adjust it as so to ease in identification. Then let us rename it. So what enters is the hot fluid. So we'll call it hot styrene. And what also enters is cold toluene. Then when hot comes in contact with cold, it becomes cool. So we'll call it cool styrene. And when cold comes in contact with hot, I would like to name it as warm toluene. So, afterwards, we need to specify our inlet conditions. The inlet of styrene, hot styrene, is 70,000 kg per hour with a 3.5 bar pressure and a 423 Kelvin temperature. And the compound amounts is just pure styrene. So, just put here 1 and 0 and click accept. Alright, so double check. Pure styrene, and then this one is 423 Kelvin, 3.5 bar, and 70,000 kg per hour. For the toluene is 50,000 kg per hour with a pressure of 6.5 bar, and lastly a temperature of 308 Kelvin. Then the compound amounts must be that toluene is purely toluene, so 1 and 0, accept. Double check, pure toluene stream, pure toluene stream, and then the temperature is 308, pressure is 6.5, and mass flow is 50,000 kg/h. So the inlet streams are finished. Now we go to the heat exchanger details. So it says here that the problem states that it is in a counter current configuration. So we'll just leave it as is. And then we need to set it as not a simple heat exchanger, but a shell and tube heat exchanger. That's why we need to change this calculation type into shell and tube's exchanger rating. We also assume that there is no heat loss to the environment. And we will ignore LMTD error. And no, I will uncheck the LMTD error since in my hand calculation, I assume that the LMTD has an error so that it will be as much as accurate as in the calculations. Then I edit the shell and tube heat exchanger properties. The shell in series, so going back, this is where I summarized everything. So in the shell details, there's only one shell in series. There are two shell passes. The internal diameter is 990.6. The fouling factor is 0. The baffle spacing is 250. The baffle cut is 25%, and that is all for the shell details. For the tube details, the internal diameter, we're not given the internal diameter, but we are given the thickness and the external diameter. So the thickness T is equal to outer diameter minus inner diameter. And also noting that the outer radius minus inner radius, sorry. The thickness equals outer radius minus inner radius, as you can see here in this type. And then radius is equal to diameter divided by 2. This means that using this relationship, noting that the external diameter is 60, that means 5 equals 60 divided by 2 minus x over 2. In order to find the inner diameter is 50. Alright, then the length is 5. The fouling factor is 0. The roughness is 0.045 millimeters. The thermal conductivity is 70. Tube thermal conductivity is 70. Passes per shell is 16. And then the number of tubes per shell is 1024. The tube spacing is 75 millimeters. And then the tube layout is square. Lastly, the fluid in the tubes. If the fluid in the shell is the hot fluid, then by logic, the fluid in the tubes is the cold fluid. So that is all. I press enter again. And we finished specifying our stream details, heat exchanger details. This is already identified the inlet hot and the inlet cold. All we need to do is just solve the flow sheet, and we would have a solved system. So, according to the problem, according to the simulator, the overall heat transfer area is 941.935 meters squared. The amount of energy transferred, actual energy transferred, is 2,631.13 kilowatts. And lastly, the thermal efficiency is 80.7836%. So, we need to show our hand calculations to compare whether the simulator is accurate or not. So, this is my hand calculation. So, the reason why there's a part that says obtaining simulator values in terms of outlet temperature is because if we try to solve this entire problem using the given data without knowing the data of the outlet temperature, it will turn into an iterative solution, which we were also not given the overall heat transfer coefficient, which also makes hand calculation of this problem very, very difficult and tedious. That's why, in order to simplify, we're just going to show if using the hand calculation is similar to what is shown in the simulator. So, what I did is that I used the outlet temperature values given in the simulator and the heat exchanging coefficient, this one, global heat transfer coefficient, in order to hand calculate the entirety of the system. Since I'm already given enough data, I will be able to easily hand calculate the entire system, since we need to find the area and then the heat exchanged, and then also the efficiency. So take note that, again, I use the data from the simulator in order to assist in the hand calculation. Alright, next, in order to start, we need to find the fudge factor needed to truly define the correction of the shell and tube heat exchanger. So the fudge factor can be defined using the graph found in Perry's Chemical Engineering Handbook. But in order to use this graph, we need to find the following parameters. We need to find what type of heat exchanger it is, what is the x-axis, and what is the curve, so that we can find the y-axis, which is the LMTD correction factor or the fudge factor. So how do we find the curve? So the curve is simply the hot inlet minus the hot outlet over the cold outlet minus the cold inlet. So doing a temperature ratio, substituting the values given and also from the simulator, I would be able to know the curve, which is 0.3930, or will approximate to 0.4 for ease in graph identification. Next, the x-axis variable has this formula: the cold outlet minus cold inlet over the hot inlet minus the cold inlet. So the maximum temperature difference over the cold fluid temperature difference. Doing so, substituting the needed values, I would find that the x-axis variable, or s, is 0.4379 or 0.44 for approximation. Then we need to define what graph would be used. There are many types of graphs in the Perry's Chemical Engineering Handbook with regards to the fudge factor. So I use specifically figure 11-4B, not A, not C, not D. I used the B graph. It's because it is the LMTD correction factor for heat exchangers in a 2 shell passes with 4 or more tube passes configuration. The point is that there is a 2 shell pass graph specifically, and according to the problem, the shell has 2 passes. So that's why I use this graph, graph B of figure 11-4. So using the same figure and applying, projecting the following values and curves. So my x-axis is 0.44 and the curve is 0.4. Then trying to find their convergence, it might be a bit difficult, but knowing that if you can see this curve, it moves here and converges in this line and it hits this line. So my fudge factor, using ratio and proportion in PowerPoint, I would find that my fudge factor is 0.99 approximately. So approximately 0.99. Then I will need to find the total heat transfer area. So the total heat transfer area means that the number of tube passes times the number of tubes per pass times the area of one tube. So the area of the tube, we're considering not the cross-sectional area of the tube. If we imagine that the tube is a cylinder, like so, if we imagine that the tube is a cylinder like this one, and if we consider the cross-sectional area, meaning that the heat transfer is on this one, in this part only. However, that's not the case. It's because the tubes comes in contact with the fluid surrounding it. That means we don't need to find the cross-sectional area, we need to find the surface area of the cylinder. The surface area of the cylinder is simply multiplying the circumference of a circle times the length of the entire cylinder. So the circumference of the circle is 2 pi r, or pi times diameter. And we will consider the inner diameter in terms of the area of one tube. So the tube passes, number of tube passes, we call it as capital N. The tubes per pass, small letter n, and the area of one tube is pi inner diameter times length. However, we have data for tube passes, number of tube passes. According here, the number of tube passes is 16, but we don't know the number of tubes per pass. So how do we do that? So in order to find the number of tubes per pass, we need to find the number of total tubes over the number of tube passes. And since n and n, the n variables cancel out, leaving the number of total tubes per shell, and this data we have, which is 1024. Therefore, substituting everything, and since this is the inner diameter, we have the inner diameter, right? However, noting that we're only given, if we're going to base it on the given, specifically, we're not given the inner diameter, we're only given the external diameter. Well, in order to find the, since we're already given the thickness, saying that going by the equation that I said earlier regarding thickness and diameter, I would use this formula, where essentially it's just also 50 millimeters of inner diameter, but doing so properly in a mathematical way, it is substituting it based on the given data. So, substituting this formula and substituting a mass substitution and overall converting this millimeters into meters so that it will be given a meter squared value, I would calculate that a total heat transfer area from my hand calculation is 804.248 meters squared. Then, finding the heat capacity of the hot fluid styrene, I find the bulk temperature is the average temperature between the inlet and the outlet, as you can see here. In order to find the fluid properties, it is 413.1035 Kelvin. Then finding its heat capacity using Paris Chemical Engineering Handbook, we'd have 225,604 joules per kilomole per Kelvin. Then finding the heat capacity. This is the specific heat capacity. Finding the heat capacity simply is the capital C times mass times specific heat capacity. So knowing that the mass of the styrene, the mass flow rate of the styrene is 70,000 kilograms per hour, then multiplied by our recently calculated specific heat capacity, converting it into kilogram to kilomole by courtesy of its molar mass, and converting hours to seconds, I would calculate that the heat capacity of styrene is 42,119.52 watts per Kelvin. The reason why it's watts is because joules per second is also equal to watts. That's why it's watts per Kelvin. Doing the same procedure in terms of toluene, where we'll find the average temperature of toluene in the inlet and outlet, finding its heat capacity with respect to Paris Chemical Engineering Handbook, and finding the heat capacity, this is specific heat capacity, and this is the heat capacity of toluene, and noting that the toluene mass flow rate is 50,000 kilograms per hour, as seen here. 50,000 kilograms per hour. I would calculate a heat capacity of 225,104.94 watts per Kelvin. Same units. Then, we need to do a comparison. So, between the heat capacity of styrene and the heat capacity of toluene, the bigger one is styrene and the smaller one is toluene. This means that the heat capacity of toluene will act as the minimum heat capacity, and vice versa, the maximum heat capacity is the heat capacity of styrene. So how do we find the effectiveness or the efficiency of the entirety of the system? Well, this equation is used whenever you're not given the outlet temperature. Well, it might be quite ironic to say that why would we use this equation if this equation is specifically used for unknown outlet temperatures, but we use the outlet temperature from the simulator? Well, it's because this is in terms of the problem statement, since initially we were not given any information whatsoever regarding the outlet temperature. So in order to truly be consistent in calculations, I use this formula, which again requires only the does not require the outlet temperatures, only the overall mass transfer coefficient, heat exchanger area, which is I calculated earlier, the minimum heat capacity, which is the heat capacity of toluene, and the maximum heat capacity, which is the heat capacity of styrene. So substituting everything, doing so, we have this value, and converting it into percent form, I would find that the effectiveness or heat efficiency for counter-current flow of this shell and tube heat exchanger problem is 91.12%. Then finding the actual heat rate is using this formula, effectiveness times the minimum heat capacity times the maximum temperature difference, which is the hot inlet minus the cold inlet, or T1S minus T2T. So substituting everything, and the minimum heat capacity is the heat capacity of toluene, 25104.94, and the maximum heat difference, maximum temperature difference based on the given, which is 423 Kelvin minus 308 Kelvin. And converting it into kilowatts, I would find that the actual heat rate is 2,631.76 kilowatts. Alright, so this is the values that I obtained from hand calculations, and these are the values I obtained from DWSIM calculations. So let's double check if these are the DWSIM's calculations. So the heat exchanging area is 941.935 meters squared. The simulated heat exchanging area. The simulated heat exchange is 2631.13 Kelvin. Sorry, 2631.13 Kelvin, and the efficiency is 80.78%. So doing a percent difference in terms of heat transfer area, I'd find a percent difference of 15.77%. Quite a bit large. And the percent difference of the energy transferred is around 0.02%. So very, very small. I was surprised when I calculated this earlier. And lastly, the energy heat efficiency or effectiveness difference is 12.03%. So quite also large. So it might be a suspicious result when the percent difference of the heat transfer area and energy efficiency is very large compared to the energy transfer, which is very, very small. So the main reason that I can give, the reason for this main difference in variation is that the comparison between hand calculations and simulations shows a bit of variation. This may be due to the different assumptions used during calculation, as well as the hand calculations using the DWSIM results for its preliminary start. So remember earlier that I used the data from DWSIM in order to truly justify the simulator itself. So it's quite ironic that in order to justify the values of simulator, I used the simulator values in order to use them for hand calculation, which may cause a bit of variation. Since again, the reason why I use the simulator values rather than doing it manually from start to finish without the help of the simulator whatsoever is because there's a lack of data and information, as well as if I actually try to push through with this hand calculation, it would turn into an iterative solution and a very tedious one. The reason being it's not like I don't like tedious solutions, it's just that this solution requires the use of a graph. And doing a repetitive iterative solution that does not have purely mathematical equations that requires the use of a graph means that for every iteration, I would need to use a graph manually, then input that value from that graph and do the same as well. So again, we don't know how many. I didn't dare to try it because again, the tediousness is very, very large. That's why I use the simulator values for my hand calculations. But overall, it's not actually that bad. It's because 15.77%, 0.02%, 12.03%, it's not greater than 20%, because greater than 20% or greater than 30% is a very, very suspicious value when hand calculated compared to the simulator. But this is not bad, because regardless, it shows us an estimate on what do we expect when we calculate it by hand, and an estimate on the simulator in terms of its configurations. So overall, these are my values for hand calculations in DWSIM, and the variation again may be due to the fact that again also another cause of difference is maybe the property package is different from my assumptions, because the algorithm uses my algorithm or hand calculations uses a different set of assumptions compared to the rigorous calculations used by the DWSIM, also noting that the DWSIM notes that the property package used is Unifac, while in this calculation, I just based on what data was given to me, also from the data from the Paris Chemical Engineering Handbook. So those are the important notes from my algorithm calculations and DWSIM simulators. And overall, it is a good estimate of between the two methods. And again, my name is Dayap. Thank you all for listening, and I'll talk to you all later.